Okay, I've just hit start webinar, and we have the list of attendees coming in. Okay, well, welcome to the Balticon 55 presentation, excuse me, recycling from stars to starship by Jim Beall. And thank you all for showing up. He has decided to take questions at the end. So if you have a question for him, please type it in either the chat or the Q&A panel. Notice that I have the live captioning on. US participants can turn that off if you want to. Other than that, please take it away.
Well, good morning. My name is Jim Beall. I'm a nuclear engineer, have been for about 50 years, I guess now. I have done everything in the nuclear and energy field, from designing, operating, regulating, constructing and deconstructing nuclear power plants. And I've been at nuclear plants in more than just our own country, and more nuclear facilities than just reactors. But I've been an avid science fiction reader for even longer than the 50 years. And since I retired from my agency, the United States Nuclear Regulatory Commission, I've been writing a lot of science articles. And one of the ones I want to talk about today is recycling. And I'm going to cover from stars to starships. On the left is what was in the past a star. On the right is what might in the future be a starship, but one that would take generations to get from here to any other system. Now, this is going to be a bit of a different take on recycling than perhaps you're expecting, and this may not be the last reference to science fiction. I picked this image because it is where recycling first began, and it continues today. After the Big Bang, the very first stars to have formed would have been almost entirely hydrogen, a little helium, and trace amounts of lithium and possibly beryllium. When those stars completed their fairly short life cycle, they had a supernova, and they threw all that mass, a great deal of mass, out into space, where over time they were to be swept up and be part of another star, the hydrogen, the helium, and the heavier elements that it produced from fusion. That next generation of stars was called population 2 stars. And they would have about 1/10 of 1% of their mass would be elements heavier than hydrogen and helium. When those stars completed their life cycles and had another stellar event that ended it, their material would again be swept up by later stars. Stars like our sun, which is a population 1 star, which by definition at this point means it's about 2% of matter is heavier than hydrogen and helium. And what that means is our star is a product of recycling, but our star was formed from the materials of the solar system. So our solar system is a product of recycling, and that includes the Earth. And that includes oxygen, carbon, iron. All of those are products of recycling, which means our bodies, we ourselves, are products of recycling. As Carl Sagan famously said it, we are made of star stuff. He could have said we are made of recycled star stuff. Take to the next slide. What you see going on in this image is the universe's greatest recycling engine. All that matter that I mentioned is being thrown out at great velocity to eventually be captured and be part of other stars. But it is not the only such recycle engine. Another example of a massive recycle engine is nuclear star collisions. They eject mainly very heavy elements far down the periodic table, and they do so in such great masses that scientists don't try to describe them in tons. They don't even try to describe it in kilotons. Instead, they've created a unit of measure called Earth masses. In the famous August 2017 event, which produced measurable gravity waves, why it was so celebrated an event in the press, it threw out tens of thousands of Earth masses of heavy elements, including, by the way, 10 Earth masses of just gold and platinum. to give you an idea of the recycling going on. Now, I said that the Earth was a product of recycling, but that's not all. The Earth itself has always had its own recycling engine. And what you see there is an overview of that engine. You see about 5 to 6% of the Earth's crust has been recycled. We can tell that because there's a distinctive ratio of germanium and silicon in remelted mantle. And they took 30 samples from various mid-ocean ridges all around the planet, and they show a consistent ratio of melted and remelted mantle. And the only way that could have been there, the scientists say, is if the engine we're looking at right there had been in place and operating for most of our planet's history. Now, I'll let someone else give you another explanation.
I'm literally at the boundary of creation in Iceland. On my left is the North American plate right here. I can put my hand on North America. I can reach over here and put my hand on the Eurasian plate. And this is the very spot where the Earth is spreading open, about an inch a year, about your height in your lifetime.
When two plates are spreading apart in one section of the world, other plates are moving toward each other in a different area, forming a convergent plate boundary. At these kinds of plate boundaries, one plate can slide underneath the other in a process called subduction.
Subduction is a key piece of the recycling engine of our planet. It seems pretty obvious that that must be happening, but science has only recently accepted it. Map makers and explorers like Magellan had long noted that certain shapes of certain parts of continents like South America and Africa looked like they should fit together, or perhaps once fit together. And geologists commented, quite notably in the various documents, that the geology along what would have been those matching edges was remarkably similar. And paleontologists noted that there was a lot of fossil similarities along those same edges. But mainstream science, refused to accept what was then called continental drift. Richard Attenborough describes this situation when he was recounting his university days in the 40s. He asked one of the lecturers why continental drift was not in the lectures. And he was replied sneeringly, the reply he got was, until someone can come up with a force that can move entire continents, it's all moonshine. Well, in the mid-60s, they found those mid-ocean ridges and the spreading going on the ocean floor. And with that kind of incontrovertible empirical evidence, science completely reversed course and accepted it, and it became plate tectonics. Now, no sooner had science accepted it, within a few years, science fiction was using it. Larry Niven, for example, in Protector in 1974, he has a very advanced race having to evacuate their planet. And the last ones to leave don't have enough metal for their ships. So they get them off the planet and cause catastrophic tectonic events so they could get at more metal to make their spaceships. David Brin describes and uses subduction in his stories, including the Tides of Kithrup, which became Star Tide Rising, and Uplift, who are both great books, award-winning books, in which he stated that it was the duty of a sapient race to outgrow its planet and to leave it so that subduction and plate tectonics in general could renew the surface of what would now again be a fallow world that could perhaps regenerate enough to create another sapient race. It was your duty as a sapient race to leave your planet and let subduction and plate tectonics renew it. I want to turn to man. Whether it's fashioning huts out of reeds or making tools out of bone, humans have always recycled. And that brings us to, as I see here in the picture, 3 of the 7 wonders of the ancient world. I don't know about you, but I would like to see these, but I can't, nor can you. Hanging Gardens of Babylon, built somewhere in the 900 to 600 BC range. It was described glowingly by some of the people that saw it, but no one knows where it is or was. And some historians are now doubting it ever existed, because you see, it was recycled so thoroughly that we don't even know if it even existed. The Colossus of Rhodes, a 108-meter tall bronze statue. That means the statue was about the same size and height as the Statue of Liberty in New York. Colossus, by the word, comes from the Greek word meaning statue. So it didn't originally mean something huge, it just meant statue. But if you said the statue of Rhodes, no one had any doubt what statue you were talking about. It took about 12 years to build, started in 292 BC, completed in 280 BC. It stood for 54 years. And then an earthquake, Mediterranean was shaken by a lot of earthquakes over time, toppled it. They talked about rebuilding it, restoring it. But an oracle said that the god Helios, which is who the statue was supposed to be looking like, was displeased. So no one wanted to risk displeasing Helios further. So they left the statue right where Helios put it, on the ground. And it stayed there for like 850 years until 653 AD, when the Arabs conquered Rhodes, the island of Rhodes. And well, Helios wasn't in their religion, and the Greek culture wasn't their culture. So they sold the bronze where it lay on the ground to a Jewish merchant who, not his God, not his culture. And 900 camel loads later, there was no more Colossus of Rhodes. We know it existed, so it's better than the Hanging Gardens of Babylon. We don't know exactly where it was because it was recycled that thoroughly. And we don't know what it looked like. But I can tell you as an engineer, it did not look like that picture, because the bronze and other metallurgy of the day would not have allowed a statue to be built that tall, of that much mass, with its legs apart like that. It would not have looked like that, but we don't know what it looked like. But still, we know it did exist. The third one's the Temple of Artemis. This was built originally around 550 BC. Various catastrophic events occurred. It was rebuilt twice. It was 2 times the size of any of the other Greek temples. But it was finally destroyed in 401 AD, and its ruins were quarried away by Christian churches who were building their own places of worship, not their religion, not their culture. But we know exactly where it was because some of the little bits are still there. But we would know more, we'd be able to visit it, except they were all recycled. Now I'm going to look at a few that were not recycled. Let's take the Pantheon. Main reason perhaps why it never got recycled. There are others, but this is the main one. It's been in continuous use ever since it was completed in 100 something AD. I'm going to be speaking about the Pantheon, like I said, a bit, but there's a little part of it I want to point out right now. Notice the front of it looks like the Parthenon, which was the temple to Athena. And that was deliberate. But notice in the Greek worship, the temples were not places where the worshipers actually went inside to worship. They stood outside the temple and watched the priests and the priestesses inside conducting the rites. But in the Roman Pantheon, you walked into the Parthenon part of the temple, and you walked into this tremendous dome. And inside there were the niches and altars and shrines to all the gods, Pantheon meaning all the gods. You were welcomed in to worship. This is very indicative of the Roman theology in general. It's very inclusive. If their legions conquered your country, they didn't try to take away your religion. They, in fact, tried to find out what gods you did worship. If you worshiped a god of wine, say, they would say something along the lines of, we worship this same god. In our land, he's called Bacchus. What is he called in yours so that we may worship him properly in your land? Or you might say, they might discover you have a god that is not in their pantheon. You might say you had a god of streams and they didn't have one. They would say, this is wonderful. Tell us more about your god of streams. We would like to build a shrine to him and worship him here in his world, in his country, your land. So Roman legions would conquer you and you would have problems, but religious wars were not something that was common within the Roman Empire. There would be no divides. So that's kind of why the Pantheon survived, because when the Romans adopted the Christian religion, they turned it into a Christian temple, and it's now the Christian religion. So they didn't recycle it. Go on the next one. Machu Picchu. This was built in the 1400s in Peru, what is now Peru. And so it predates Columbus. It was made of large, dry stone blocks fitted together without mortar. Very valuable building material. But all the material is still there. And the reason why, you can see from the picture below, it is so remote and so hard to get those materials anywhere else that they just left them there. And they're still there. Plank, Mexico. It was never recycled. It flourished between 200 and 800 AD, but it was basically abandoned around 800 AD. Why? Was it war? Was it drought? Was it plague? Was it climate change? No one is sure, and there are many theories. It covers over a full square mile. As of to date, only about 10% has been excavated so far. But basically, it remained preserved because no one knew it was even there. It pretty much got forgot. Now there's another one I want to talk about, Angkor Wat. It's not one of those three, but it deserves special mention. It's an extensive area of buildings, many of them religious. The area was conquered by an external conqueror, and they took what they wanted, looted, and they left. The culture pretty much never recovered to its previous state, so they didn't really need the stone. So they pretty much left it there. And it was the same basic religion as the people who were still living there. So they had no particular incentive to despoil it for that reason. And so the people who live there now in Cambodia, they have restored some, but some of it they've left pretty much as is, just stabilizing it and leaving it with the trees overgrown just like that. You can see there's been little change in some of those places since it was first photographed by Western explorers in 1866 and 73 and today. I want to turn now to another one of the ancient wonders of the world, pyramids of Giza. They used to originally look like the one on the right, bright and shining white. They look like what you see on the left now. Why did it look like that then? And why does it look like this now? Notice that, millions of man hours. And that is just for those high quality casing stones that were so carefully engineered and fitted together that there was almost no cracks that you could see. They looked like a shiny white side, completely flawless. So what happened to all those casing stones? Well, a few of them are still there. There's one of them. You can see the picture taken in 1912 and to the picture today. You can see it's the same casing stone because you even have the same graffiti down there. What happened was in 1303, there was one of the many earthquakes in the Mediterranean. A very great one occurred in 1303, and it centered around the island of Crete. It shook the Mediterranean, and one of the effects was in Egypt was it opened cracks in the casing stones, dislodged them slightly, but made enough of a crack so the pry bars could get in between the casing stones. 1303. By 1365, almost all the casing stones were gone, recycled into mosques and other buildings in Cairo. Remember, not their culture, not their religion, so it was theirs to recycle. And by the way, that same earthquake in 1303 is what pretty much demolished what was left of the great lighthouse of Alexandria, which, by the way, was another one of the 7 wonders of the world, ancient world. So next one I want to turn to is this. What is it? This is a highly polished, meticulously engraved, lovingly engraved piece of white limestone. Note that the museum curators who are holding it are using white gloves so that they won't get any dirt or hand oils on it. It's estimated to be about 3,400 years old. Down over to the left, you can see the headdress of the goddess Sheshat, ancient Egyptian deity of writing. And the hieroglyphs above it contain their traditional attribute, which is mistress of the house of books. So obviously, it came from an ancient Egyptian temple or shrine. But why did it get chipped into that roughly trapezoidal shape? Why did someone drill or punch a hole through it? I'll give you a clue. It was found in the mud, in the seabed, off the port of Haifa, by swimmers, just saw it. The answer is that it was turned into a boat anchor. A highly valuable object was recycled, but into something of very low value. Now, the use of other pieces of stone for anchors was common in that era. As you can see, there are many examples. But again, you took a valuable object and you recycled it, but only by using it in a very non-valuable way. So we can detect that it was recycled. There are other ways to detect that buildings are recycled. Here's a very prominent one by aerial archaeology. Recycling may make the building vanish from the historical record, like the Hanging Gardens of Babylon. But you can sometimes still find they were there because they can leave lasting detectable footprints in the environment. On that picture on the left, you can see where the roads were because it's so much shallower there for the soil. So in periods of low moisture or drought, they become white. You can almost see the wall lines, the blueprints of the buildings on the ground. Places where it's darker green, there might have been a foundation that has been robbed away for the stone, because stone was always valuable. And so that the soil is actually deeper. This is used a lot, by the way, in a British TV show called Time Team. It ran for 20 seasons, over 300 episodes, and extensively explores some British archaeology, a lot of them found by means like this. And you don't even have to have stone buildings to be able to use this technique, by the way. Here is a typical Iron Age roundhouse site. It too was recycled. You can see that the ditch is darker because it's lusher vegetation is growing there. You can see where it's lighter, where the stone parapet's been smoothed out. And you can see dark spots where they had fires and stockades and animal places. So why would you not recycle? Why don't you want to recycle? Is there a reason not to recycle? I'll give you a clue. A great many travelers came from all over the world to visit Rhodes to see the Colossus as it lay on the ground for the 800 some odd years it laid there. After the Arabs sold it to the Jewish merchant and recycled it, they stopped coming. Archaeotourism. It's not just the ancient world that does it. We've been doing it in the recent years. Here's the Great Pyramid photo op. You can see that the Victorians were being part of the Grand Campaign, the Grand Tour, and it was very popular then and all throughout that period. Now, why would you do archaeotourism? Because it allows some very cool, unique experiences. And all the people that come bring their money with them. They spend it in lodging, food, taxes, fees. They pay the guides. They pay all the support systems. Basically, they bring money to you. Egypt, let me start with Greece. Greece, with all its monuments and preserved temples, it derives even today about 1/4 of its gross domestic product from tourism. Egypt, which is where these pictures are taken, obviously, had worked up to about 11% of its gross domestic product was coming from tourism. And 14% of its population was employed in that industry. But then the terrorist attacks on foreigners and tourism and visitors drove those numbers way down. Now, I said you could have some unique and cool experiences in archaeotourism. That brings us to a fairly familiar meme, which is no matter how cool you think you are, you will never be as cool as. Well, I have one for you. You'll never be as cool as these people who are having high tea while they're sunbathing on top of the Great Pyramid. And this is not something that has ended. It is still popular. And it's not just the ancient wonders of the world that attract them. Almost any unrecycled site of note will attract tourism. I mentioned Palenque before, where people just walked away from it in 800 AD and it was forgotten it was there. Well, these numbers are from the last COVID year. 750,000 people came to Palenque. Machu Picchu, which is, you saw how remote it was, you see the number of people that came to it. And the Pantheon, over 9 million people went to see the Pantheon in 2019. Now let's turn to Angkor Wat that I mentioned before. Do these photos look familiar? Perhaps they should. Here's why.
Remember that one scene in Tomb Raider?
So what you can see is that even unrecycled sites that are not restored, there's even revenue to be gotten from them. Here, they filmed movie, Tomb Raider, in the part of Angkor Wat where I had those photos. It is another reason not to recycle things. I want to turn to another phenomenon. What do these buildings have in common? We already talked about the Pantheon, which is the upper one on the left. It was not recycled, but it had bronze fittings. It had marble facings, and they were recycled. It has bronze doors, great bronze doors from the original building when it was built in 100 something AD. They're still there, but they were reinscribed into Christian symbology, so they did not get recycled. It had vaulting in the Parthenon section that was made out of bronze. One of the popes in the 1600s decided that he wanted that bronze to be used for something else, perhaps in the altar place at the great Basilica of Rome. And so that's gone. But in place are timbers. So if you go in that section of the Parthenon and Pantheon and you look up, you will see timbers from the 1600s. On the lower left, you'll see another shrine in Rome. And on the far upper right, you'll see the great Colosseum in Rome. It too had a lot of marble fittings. And all the seats inside were sheathed in marble. The marble's gone, but the building's still there. The building on the lower right is another Colosseum. This one's from Nîmes, France. The Romans, by the way, built about 230 Colosseums we know of. They were basically Netflix and YouTube and everything else combined for them. That's where they did entertainment. And this brings me to another building, also in Nîmes, France. This one I put in a special case because it's kind of near to my heart, because Thomas Jefferson so admired that when he was the ambassador to France in 1785, that he had a stucco model made of it. And he used that model for designing the Virginia State Capitol. So the reason why these buildings were not recycled is that they were made out of concrete. Rome was not the first to come up with the idea of concrete, but they basically rediscovered it, and then they perfected it. And they were the first to use it on a very large scale. And this is good. This is important, because any population that's growing in numbers, like the Roman Empire was, and standard of living, like the Roman Empire did, consumes increasing amount of quantities of materials. Whole forests probably owe their continued existence to concrete. Entire areas would have been quarried away to try to quarry the stone away to build their buildings. But concrete the Romans used volcanic ash and high temperature kilns, 1700 degrees Fahrenheit. But the thing about concrete, it's kind of hard to make until you learn how to do it and you perfect it, but it cannot be usefully recycled. It simply becomes rubble, dirt, dust, if you try to recycle it. So if you conquer a place and there are concrete buildings, the occupier, the new owners of the building, pretty much have two choices: use the building as is or repurpose it, or demolish it, and all you've got is a lot of effort to do it, and you've got nothing but rubble left of your efforts. So pretty much you leave it there. That's why so many of the Roman buildings have survived. The knowledge of how to make concrete was lost with the fall of Rome, and it remained lost for over 1,000 years. It wasn't until somewhere in the 1400s that someone retranslated a Roman treatise from AD 15, that's 4 centuries before Rome fell, on how to make concrete. Once that knowledge became known, people began experimenting with it again, but the very first building to be made out of concrete was made in France in 1499. So if you ever want to write another alternate history, by the way, and you want an easy change, all you got to do is have someone retranslate that document sooner. And it wouldn't be hard to do. They've identified so far 78 copies of that same treatise that survived the Dark Ages and the Middle Ages, all those ages that were still around in the 1400s when the one was retranslated. What effects would this have? Well, remember those great basilicas, cathedrals in Europe that took hundreds of years to build? The Romans built the Pantheon in under 10 with concrete. Think of how the basilicas would have been built then. Castles. You don't have to get all these stones to build castle. You use concrete. How would history change if you can make a castle or a basilica so much more quickly and so much easier? Now I'm going to start exploring some other materials for recycling. We're going to start with glass. Glass blowing was developed in the area now known as Syria, somewhere around 100 BC. And Romans conquered it in 63 BC. Said, this is great stuff, we want to use it. They turned that entire area into a mass production center. But they brought back all the secrets on how you make glass and the artisans who were making it back to Rome. And they kept that secret pretty close. But a lot of glass got made. You can find glass objects and shards all over the Roman Empire. Archaeologists are coming up with it in sites all the time. And let's explore one of those areas. Rome invaded the Isle of Britain in 43 AD, and he pretty much stayed there for 400 years. Archaeologists, like I said, have found tons of glass in Britain, but they've never found any place where it was made. They have found places where shards were collected for it to be remade, because remaking it, recycling glass was easy. Was making it the first time that was hard. Now, because glass is fragile, what that means is they were probably constantly remaking broken glass, to the point where probably late during the Roman occupation of Britain, probably almost all the glass that was in use there was recycled glass all the time, easy to recycle, reuse over and over again. And the Romans just didn't stay with what they learned in 63 BC when they conquered Syria. They got better at it. They made really nice, pretty, wonderful objects. And they made even better objects. They got better and better and better at it. And they got even to this far, like Lycurgus cup. This is what's called dichroic glass. We did not figure out how they even made this stuff. You see, when the light is behind you and you're looking at it, it looks green. But when the light's behind the cup, it looks translucent and red. How did they do it? Well, they got a little piece, they put it under an atomic force microscope and found that it had very tiny colloidal bits of silver and gold suspended in the glass. The bits were so tiny that some people have called it the first deliberate nanotech. This would have been around 400 AD. So Rome fell, glass was relearned, and got used by the modern world. What did we do with it? Well, we made it cheaper and cheaper. And until it got to the point where it became no longer a luxury product, but a common product everywhere. Everybody had it. We use it everywhere. We've made a lot more glass than Rome ever did. As I said, it went from a high status object to basically a common day prosaic one. But it was always remained almost perfectly recyclable until we started making it better. We started finding ways to use polarized, make it higher temperature, higher pressure. We made it so it wouldn't shatter as well for safety purposes. We basically made specialized forms of glass for the first way we used it. But guess what? Because we made it specifically optimized for its first use, we made them all sufficiently different in physical properties that it's very difficult to recycle mixed lots of glass. If you try to recycle it, you don't get a quality product. It is not as recyclable. You pretty much have to segregate it into the same kind of glass to be able to recycle it well. This is a principle that we're going to come back to again. But before I do that, I want to turn to aluminum. Aluminum originally could only be produced by a tough and expensive sequence of chemical processes. As a result, when it originally began to be used, it was scarcer than gold and worth more than gold. And unsurprisingly, when we decided we wanted to build a Washington Monument and put a unique and special top on it, aluminum, it didn't tarnish, seemed to be a very natural, elegant choice. And in 1884, the 9-inch, 100-ounce casting that was put on top of the Washington Monument was the largest piece of aluminum in the entire world. It was so valued that Tiffany's of New York exhibited it. They put it on the floor of their store in New York, put ropes up around it, and invited the public in to step over it. And they came in the hundreds, they came in the thousands to step over it. So they could say they were stepping over the tallest building of the world, in the world. And in 1934, they checked on it again, as you see the picture. It's still there, untarnished. You can see the inscription is still readable. 50 years after that, on the 100th anniversary, centennial, they reenacted at Tiffany's and they lined up to step over it again with a fresh casting. And by the way, it's still there. We spent Spider-Man to check on it in 2017. Now, I mentioned aluminum because recycling aluminum takes only 8% of the energy needed to refine it from the bauxite ore. And that makes it very attractive economically to recycle. And as a result, it appears that 75% of all the aluminum that we've ever made is still in use today, most of it recycled aluminum. Go to steel. Where would we be without steel? We use it for everything: buildings, vehicles, pipes. According to the Steel Recycling Institute, steel is the most recycled material on the planet by mass, more than all other materials combined. And about 86% of all steel gets recycled. Yet despite that, our appetite for steel is so vast in our planet and our standards of living and a growing population that, just like the Roman Empire, we are forced to make new steel. And in fact, 1/3 of all the steel that is currently being made today is made out of new materials, new resources, raw materials, even though we are recycling 86%. I want to turn next to another common product that we deal with every day, and that's tires. Originally, tires were basically natural rubber. As you can see by the poster, it was essentially a luxury product. And it was recycled because, as you can see, that by weight, it was worth about the same as silver. It didn't last long as tires, but that was okay. You could recycle them. Then automobiles came along, and the demand for tires got huge. And not just the demand for tires, but the demand for better tires, because they weren't just bicycles riding on these tires anymore. They were heavier automobiles, trucks. They weren't just traveling a few miles on trails, they were on roads for long distances. Durability became important. So the inventors made better tires. They introduced fibers. They perfected artificial rubber. They put steel belts in it and a whole bunch of other things to make tires better. They became cheaper. They became longer lasting. They became very tough, and they became very hard to recycle. And we get this. In 1990, we're an estimated 2 billion used tires laying around in piles around our planet. Half of the 1 billion were in the United States alone. One pile in Colorado alone was estimated to have 75 million tires in it. And the environmental concerns associated with this led to a lot of regulatory changes and incentives for recycling. What kind of environmental issues? Well, not only did there the ones you would expect, but ones like this. Because see, each tire is about 7 gallons of oil. Recycling is tough, and as a result, up till recently, most of them have been simply burned. But that's environmentally challenging to burn usefully without giving off a lot of hazardous material. So basically, it was turned from a high value product into a fairly low value product, fuel, ersatz fuel. Other places were using it as rubberized rubber, like for playing fields and things like that. Again, you're taking a high value product that took a lot of energy, efficiency, and resources to produce, and you're using it for a low value option. Remember that anchor from earlier before. So we were stacking them up, and there's a twist. You see, concrete makers, remember, we're still using concrete even more than Romans ever did. They had been using coal ash from the power plants. That is, they were recycling coal as the ash to make concrete. The Romans used the Pompeii and Vesuvius volcanic ash. We were using coal ash from coal power plants. But the environmental efforts to reduce coal plant power use has led to a drop in the amount of coal ash being created, which is not a bad thing, mind you. But now we're getting to the point where concrete makers are having trouble getting enough ash to be able to make concrete. It turns out that you can recycle tires into such a way that you can use the ash product for concrete, and we're beginning to do that. However, it's a very high temperature process. I told you how the Romans used 1700 degree Fahrenheit kilns. It takes 2800 degrees Fahrenheit to recycle tires, and a lot of electrical power. It takes very large, powerful machines, huge machines, to grind them up into the feed that you can feed in to be able to burn it in such a way that you can use the mix, the ash you created to be able to make cement. But nonetheless, we have worked down the great inventory of tires around the planet. But it doesn't mean they're gone, because we discard hundreds of millions of tires every single year. There are still large piles around the planet, and I'm going to show you one. It's so big still, it's visible from orbit. Here it is on Google Earth. You see, a stopgap measure that many developed countries used was it was so costly to recycle tires that they basically shipped them off to third world countries. And they stacked them up in deserts and stuff like that. So those piles still exist. Those fires are still happening. Enough on tires. Let's turn to a nicer object, nicer material. We'll turn to gold. Gold's always been valuable. It's always been desired. It's always been valuable. It is easily recycled, and it does get recycled. In fact, anytime a place gets conquered, all the priceless art and religious artifacts that are made out of gold from that culture are melted down. Think of all the golden artifacts and treasures of the Mayans and the Incas and the Aztecs that became Spanish coins. Remember, not their culture, not their religion. So they become gold, they become coins, recycled. However, recycling gold has what might be an unexpected twist. Its very high value means there's an incentive not to use very much of it. The Egyptians loved to display objects, golden objects, but a great many of their golden objects are already very thinly coated with gold. They didn't have electroplating, but they had found ways to mechanically make it down to almost the micron level. So a lot of artifacts would have to be destroyed to be recycled to get much gold. This is a principle we're going to see again as well. Turn to another problematic material, plastic. Plastic seems to combine all the worst attributes of recycling. Like glass, if it was all the same kind, you could recycle it, but it's not. If you try to recycle mixed kinds together, you basically get low value rubble, like concrete. You try to use it as thin as possible. So any one object doesn't have much to recycle, like gold. And like tires, it is the easiest way to recycle is simply to burn this stuff. It's low value, hard to deal with hazardous material, but you burn it. That's how you recycle it. And it's so difficult to recycle, it's basically coating our oceans now. Turn to another one. This is a new type of recycle problem, the acronym WE. You see, personal electronics contains a lot of valuable materials, but only applied in very tiny amounts. Recycling is very tough. Most processes involve a great amount of energy. They produce large volumes of hazardous waste. I'm going to show you some stats. Now, I'm not going to read these stats to you, just look at them. But notice how short the average lifespan of a smartphone is. The smartphone contains 200 times more gold than the ore does that you mine gold from. But that process doesn't produce hazardous waste. Trying to recycle the smartphone does. Now, that's going to be a problem that's only getting larger and larger as more people have personal electronics. As the accessibility to personal electronics increases and the lifespan becomes shorter, this process will, pardon the pun, mount up like tires. But we have to face another item, by the way, and that is we're going to have to face recycling ourselves. We're approaching 8 billion now. You can't avoid the topic. Science fiction, I've mentioned science fiction a few times before, is one of the tools we use to explore possible issues, and it has explored this one as well, from organ banks to Soylent Green. But we too, our bodies, involve recycling challenges. I'll give you an example of one. In Britain, they had to shut down all the crematoriums for a while because they found they were emitting hazardous amounts of mercury vapors, dental fillings. As I say, twists and turns of recycling are many and they're unexpected. Now I'm going to go back to the second image on my first slide, and that is the Starship. If we don't have faster than light travel, we're talking multi-generations, hundreds of years. You're not going to have new resources. You're not going to find any new resources. You're stuck with what you take with you. And also, you're stuck with your trash. You can't stash it. There's no place to put it. You can't even space it because you're going to need that mass for reaction mass whenever you get to your destination. What that means is you got to maximize recycling. And more than that, you're going to have to work backwards from recycling. That is, if you have to wear less comfortable clothes instead of artificial fibers, that's what you're going to have to wear. If you're going to have few or no personal electronics, or the ones that you have are less capable or not very ergonomic, and those are the ones you're going to have to have. There are going to have to be a great many sacrifices made if we're going to travel to the stars. And even if we don't travel to the stars, we're still going to have to do that. Because face it, Earth itself is essentially a starship traveling through space. We're going to have to recycle better. And I'm done. Done the presentation. I am open to questions at this point. Where's my person looking for questions?
I see no questions either in chat or in the Q&A, but I do see at least one great presentation.
Well, thank you very much.
And we have a comment. We need to make smartphones more modular so your thesis boat upgrade them instead of replacing.
That is a good point. And it is quite possible that some more modularity might reduce the issues, but I suspect it won't solve them. It'll just buy us time. Buying time is a good thing, but we will have to figure out how to recycle these things.
There is now a question. How does reduce and reuse fall into your presentation of recycling?
How does what? Do it again?
How does reduce and reuse fall into your presentation of recycling?
Well, reuse is repurposing, and repurposing for different use is a form of recycling. You can get caught up in semantics here. Some people define recycling more narrowly as taking apart something and putting the parts together into something new. I was intending to do that. That is one part of the larger recycling concept, in my view. So I would say those are various attributes, various strategies for recycling. If there
Sorry, I muted myself so you could talk. We all have a couple of other. We have enjoyed your presentation. We have a question of how will nanobots be used to recycle things on starships?
Good question. When we have the nanobots, we'll have a better idea. I do want to note, though, that nanobots, if you're not careful, could end up like plastic. They could be everywhere and almost difficult to get rid of. So anytime you start making nanobots and using them anywhere, you better start thinking about the end game as well. How do you get rid of it? We would have been a lot better if we'd have thought perhaps more about the consequences of optimizing any material for its first use by thinking first, before you do that, how you're going to recycle it. Like I said at the end of my presentation, we need to work backwards from recycling, not try to think of how to recycle it after we've made it.
We also have a question. What's your favorite recycling examples in SF books? One of my favorites is Ethan of Athos.
Yeah, that's a good one. I can't argue that. I confess my favorite is still David Brin's we've got to get off this planet so it'll recycle itself for the next species to come after us. That remains my favorite. I guess in that same universe, they have a library which has been kept up and maintained by all the species for hundreds and hundreds of millions of years. You don't have to vend something. You just go to the library and recycle their idea.
The next question is, what is the percentage or amount of space needed for recycling plants and machines on starships?
Again, these are all engineering questions and it would be design specific. I would note, though, that if you're willing to work in a vacuum, all you got to do is build pylons on your ship and stick it out, and you have all the area and volume you want on your starship. All you got to do is figure out how you shield what you're doing. That is, if you're going at an appreciable speed of a fraction of the speed of light, there may be radiation you have to deal with, as well as cosmic radiation.
And we seem to have a pair of related questions. In Neil Stephenson's Diamond Age, matter compilers reassemble materials at the molecular level. Landfills are the perfect source. And question regarding bacteria that eat plastic.
Yeah, you know, that bacteria eat plastic is an interesting play on Larry Niven's Ringworld series. He supposed that the puppeteers were so afraid of the race that was operating Ringworld that they seeded the Ringworld with something that would destroy their superconductors. On the what was the other one?
Diamond Age.
Diamond Age, yes. The Diamond Age thing, you almost get to the same thing with Star Trek. Star Trek have their replicators where they make food and make pretty much anything you want. Those tactics, those techniques are only available if energy is a free good. Now, let that idea soak in. Free good. That is, energy is of so low value on a unit basis, you can use any amount of it for anything. That is, there's no point in efficiency anymore. You have all the energy. It's a free good. So if you can make energy a free good, you don't have to worry about anything. And that's one example of it. I mean, on Star Trek, they're converting matter into energy and energy into matter seamlessly. You can only do that if energy is a free good. No dilithium crystal is going to do that, by the way. Fusion's not going to do it. Antimatter is not going to do it.
I'm sorry, I muted myself again. We have a final claim that the Borg recycle people. Find that interesting. Anyway, I'm going to have to wrap up here. I'm going to put in the chat the invite to the continued discussion. It's in Balticon 55 server on Discord. It's in the tech and panel discussions group. I think it's the Mount Washington channel. Let me verify that. Yes, indeed, the Mount Washington channel. But other than that, thank you all for showing up. Thank you very much to Mr. Beall for your presentation. I certainly enjoyed it.
Jim Bell, and could I talk to you afterwards? Oh, Tech Overlord?
Best is to do this by direct message on Discord, because the con is going to need this Zoom channel for the next presentation.
Very well. I have a question to ask you.
All right. I am Zen Lizard over on Discord, or actually I can copy, paste that. That is my Discord ID. Other than that, I need to wrap up. Again, thank you. Thank you for your presentation. Thank you all for showing up. I certainly enjoyed it.